In this short video, we're going to derive the demand for leisure as well as the supply for labor in a very special case where we have a perfect complements utility function. So let's imagine that Zara's preferences for leisure and consumption of a composite good are given by the utility function, the minimum of leisure and 2 times consumption, where here L is leisure and C is consumption. We're also told that Zara has 24 hours per day to allocate between leisure and labor. She earns a wage rate of W dollars per hour, and the price of the composite good is $1. Our first goal is to find her demand curve for leisure. What do we need to know to answer this question? We need to know the utility function, the price of the composite good, and the number of hours available to divide between leisure and labor. How are we going to solve this question? Just like a utility maximization problem, the only difference is we will not have a value for the wage, and so our answer for leisure will be a function of that wage. Because we have a perfect complements utility function, this is going to look a little bit different. So rather than a tangency condition and a budget line, we're going to have a no waste condition where L is equal to 2C, in addition to our budget constraint, which has the standard form that C is equal to the wage times 24 minus L. Keep in mind that when we write 24 minus L, that is actually representing the number of hours that Zara chooses to work. Now we're ready to solve this question. Here's what we know: utility function, wage, price of the composite good, and the number of hours available. We remind ourselves what we're looking for. This is a really important tool. You can get lost if you don't keep reminding yourself what you're searching for. So here we're trying to find demand for leisure. So to set this question up, the first thing we need is the no waste condition. The no waste condition is that the two arguments inside the parenthetical of the utility function have to equal each other. So we have that L is equal to 2C. We'll call that equation 1. The second condition that has to hold at our utility maximizing choice, which is sort of the background of this demand for leisure curve, is that we have to be on the budget constraint. Her budget constraint has the following form: C is equal to the wage times 24 minus L. We'll call that equation 2. Now, what do? We're going to solve 1 for C. You may ask, why are you doing that? You could just plug 1 into 2. Well, because I know what I'm looking for. I'm looking for leisure. I'm not looking for consumption. So I want to eliminate C. And the only way I can eliminate C is either by plugging 2 into 1, or I can rearrange 1 and then set it equal to 2, which is going to make the math a lot easier. So we're going to solve 1 for C. That's just a matter of dividing both sides by 2. So I get C is equal to L over 2, and I'm going to call that equation 3. So the next step here is to set equation 2, my budget line condition, equal to equation 3, which is just a manipulation of the no waste condition. By doing that, I'll eliminate C and I'll be able to solve for L, the demand for leisure. So I have L over 2, which is equation 3, is equal to W times 24 minus L. So I'm setting them equal to each other. I notice that I have this fraction here, and you can carry the fraction around or you can get rid of it right away. I think it's easier to get rid of it right away. So I'm going to multiply this whole thing through by 2. If I do that, as long as you do that action to both sides of the equation, no algebra rules are being broken, I get L is equal to 2W times 24 minus L. Now I'm going to distribute that 2W in, so I have L is equal to 48W minus 2WL. I remind myself what I'm looking for, leisure, so I collect all my L terms on the left-hand side of the equation. So I have L plus 2WL is equal to 48W. I want to find L, so I have to use algebra here. I have to factor L out of the left-hand side because both terms have an L in them. When I do that, I get L times 1 plus 2W is equal to 48W. I'm finally there. I divide both sides of the equation by 1 plus 2w. I get L star is equal to 48w over 1 plus 2w. We can call this equation 4, and this is our demand for leisure, or Zara's demand for leisure. Now we're going to take what we've previously done with our demand for leisure, and we're going to derive Zara's supply of labor. How do we solve this question? We're going to solve it using the well-established relationship that exists between leisure and labor, which is the amount of hours worked is 24 minus the amount of hours of leisure. So our goal here is now to determine Zara's supply of labor. And we already have quite a lot of information about this. We know that the demand for leisure is 48W divided by 1 plus 2W, and that the relationship between labor and leisure is that labor is 24 minus leisure. So what we're going to do next is we're just going to substitute what we know about L into this relationship and simplify. So we need to simplify this equation right here. In order to simplify this relationship, we have to use a common denominator. So we have that H star of W is equal to 24 times 1 plus 2W divided by 1 plus 2W minus 48W over 1 plus 2W. So what I've done here is I've used a little algebra trick. I want to be able to combine my terms, and in order to do so, they have to be on the same denominator. So I've taken my 24 and I've multiplied it by 1 plus 2W over 1 plus 2W. What I can do from here is a little bit of simplification. I have 24 plus 48W minus 48W all over 1 plus 2W. So I can combine these two terms as I simplify because they now have the same denominator. Lucky for us, we see something wonderful has happened. 48W minus 48W is 0. And so we can rewrite our supply of labor curve as 24 divided by 1 plus 2W. We can call that equation 6 if we wanted to. Okay, we have one last question we're going to answer now that we have our demand for leisure and our supply of labor curve. We want to know, is Zara's labor supply curve backward bending, everywhere downward sloping, or everywhere upward sloping? To answer this question, we need to look at the sign of the derivative of the supply of labor. So we're looking for H prime of W. Before we take that derivative, I think it's useful to rewrite this as 24 times 1 plus 2W to the negative 1 power. And then when we differentiate, what happens? We bring down the negative 1. And we have to technically use the chain rule here. So we have negative 1 times 24 times 1 plus 2W to the negative 2, I'm so sorry, negative 2. So just, I'm not done yet, but just to recap, I bring down the power on my parenthetical. So I have that negative 1 times the 24, which is a multiplicative constant. I reduce the power on my parenthetical by 1, so it becomes 1 plus 2W to the negative 2. But then, because of the chain rule, I also have to multiply by the derivative of what's in the parentheses. So times 2, because the derivative of 1 plus 2W is 2. So we can simplify this whole hideous thing. I have negative 1 times 24 times 2. So that's negative 48 divided by 1 plus 2W squared. Well, this thing is obviously negative. If W is positive, the wage, the denominator has to be positive. And we have this negative sign in the numerator. So H prime of W is negative, which means that as wage increases, the supply of labor actually decreases. That suggests that the labor supply curve is actually everywhere downward sloping. This is a very unique result, and it's a property of the perfect complements utility function. Particularly, it comes from the fact that perfect complements utility functions have a substitution effect equal to 0. That means that the income effect of a wage increase always dominates the substitution effect, and we get a very unusual downward sloping labor supply curve.